We are going to decide if the following statement is true or false. The statement is, if B is Turing recognizable and A is a subset of B, then A is Turing recognizable. Okay, so we are going to do a proof by counterexample to show that the statement is false. Okay, so first, let's assume the statement is true. Okay, let's pick a language that is, so we're going to pick a language that is Turing recognizable. Okay, in this case, we're going to choose sigma star. Okay, sigma star is regular, therefore it's Turing recognizable. Okay, so remember, sometimes it's helpful to remember this picture. So we have the regular languages. They're a subset of the context-free languages. These are both subsets of the decidable languages. And all of these are subsets of the Turing recognizable languages. Okay, so I picked a regular language, therefore it must be Turing recognizable. Okay, so now we're going to consider the language, a language that we know to not be Turing recognizable. Okay, and we're going to pick ATM complement. So remember, this is defined as MW such that M is a Turing machine and M does not accept W. Okay, remember here that it doesn't mean that M rejects W. It just means that M does not accept W. ATM was MW such that M accepts W. This is simply M does not accept W. Okay, it might reject or it might run forever. We don't know. Alright, so not ATM. Where is not ATM in terms of subsets? Well, this is a string, right? It's an encoding of a Turing machine along with a string. It's a string. This is an element of sigma star. Okay, whatever alphabet we have that allows us to encode Turing machines and present strings, so sigma star, so actually sigma, then this particular string is going to be an element of sigma star. Okay, it's some amount of concatenated symbols of sigma. Remember that a language is a set of strings, right? ATM bar happens to be the set of strings MW such that M is a TM and M does not accept W. This means that ATM bar is a subset of sigma star. Therefore, ATM bar should be Turing recognizable. Okay, we happen to know that ATM bar is not Turing recognizable, therefore we get a contradiction. Okay, the contradiction tells us that somewhere we said something that was false, an assumption, our only assumption here, that wasn't a fact, right? We knew sigma star was Turing recognizable, we knew that ATM bar was a subset of sigma star, we showed this, and we also know that not ATM is not Turing recognizable. Okay, so our only assumption here was that the statement was true, so this contradiction tells us that the statement is false. Okay, if you're not clear on why ATM bar is not Turing recognizable, let's do a really quick proof. Okay, so we have a proof in CSE355 that shows that ATM is undecidable. Okay, Okay, so here I'm not going to go over that proof again, but we know that ATM is undecidable. We know that ATM is Turing recognizable. Okay, what does a recognizer look like? A recognizer for ATM would simulate M on W and accept if M does. Okay? So we can recognize when M accepts W, but we can't decide when M accepts W. Okay, and again, there's a proof for undecidability in the book, but we know that ATM is Turing recognizable. Something else we know, if a language and its complement are Turing recognizable, then the language is decidable. Okay? How do we know this? Let's do another quick proof. So assume we'll just call it A and A bar are Turing recognizable. Then let R and, I'm going to abuse some notation here just to keep it clear, R bar be recognizers for A and A bar given a string W. Let me say this in a different way. Okay. Then decider for A is as follows. Okay, A, let's call it D. D on input W. Simulate R and R bar on W in parallel. If R accepts, accept. If R bar accepts, reject. Okay, so to quickly see that this is a decider for A, notice that since R and R bar are recognizers for A and A bar, given a string W, it's either an A or A bar. That's the definition of complement, right? If it's not in the language, it's in the complement of the language. So either R or R bar is going to accept W. We know this for a fact. Since we're running them in parallel, we don't run into the risk of letting one or the other run forever. Okay, so in a finite amount of steps, either R is going to accept or R bar is going to accept. If R accepts, then W was an A, so we accept. If R bar accepts, then W was an A bar, and so we reject. Okay, so given any arbitrary language, if it and its complement are Turing recognizable, then the language, that arbitrary language, is decidable. Okay, so let's go back to our, so this is a little side proof. So we know ATM is Turing recognizable. If its language and its complement are Turing recognizable, then the language is decidable. ATM is undecidable, then therefore ATM bar cannot be Turing recognizable. Okay? So that concludes the proof as to why we were able to use ATM bar as an example of a language that is not Turing recognizable. And we also showed that ATM bar is a subset of sigma star, and sigma star was Turing recognizable, so this brings us back to why that statement was false. In general, you should be wary about assuming basically closure under subset. Okay, so what I mean by that is closure under subset would say if a language is in some class of languages say Turing recognizable, then all of its subsets are also Turing recognizable. We would get that if we had closure under subset. Here we don't. And in fact, we rarely do. So I'm not saying it's a hard and fast rule, but anytime you're asked about whether something holds for the subset of language, you should think very carefully. So another example where we don't have closure under subset is with regular languages. So remember that sigma star is regular. The language A to the n, B to the n, okay, is a subset of sigma star. But A to the n, B to the n is not regular. Okay, so this is just another example of why you should be careful when you're asked questions like this, to really think it through and see if you can prove that it must hold true.